Oh, thank you. Hello, I'm Haruki Takahashi. I'm a PhD student at Meiji University. I'm going to talk about our work, Expressive Fused Deposition Modeling, new 3D printing technique. So advances in digital fabrication techniques have enabled people to create their own items. So we deal with fused deposition modeling, FDM. So FDM is an additive manufacturing technology, and FDM printers have become famous. So this 3D printer forms an object by stacking up thin plastic layers on the platform. So each layer consists of a lot of load, which is fine linear structure. So because of this simple mechanism, FDM printers have several advantages. So it's of use, available material, and low cost. So today, FDM is available in the market. Basically, it is said that FDM is not so high resolution and not so high speed, but in recent years, high resolution FDM and high speed printing technique have appeared. For example, Zotrax M200 allows us to print with 90 micrometer resolution. And on the right side, a wireprint technique allows us to rapidly print a wireframe object to preview. But the attraction of FDM is not only these advantages, it's the printing error. So basically, to prevent printing error, so we have to adjust parameter settings using a helpful troubleshooting guide. On the other hand, so printing error have quite excited 3D printer enthusiasts. So they form a community to share pictures and discuss what's happened to their 3D printer while printing. So not only enthusiasts, but also artists and researchers are also inspired by printing error. So artist Lear explored the behavior of a 3D printer and its material to create a new kind of sculpture. So these objects are generally created by the printing error, but they try to control the error and pursued FDM printers' expression and capability. Okay, these are related works exploiting the printing error. Okay, first, it's my favorite work, 3D printed hair. To fabricate hair-like structure, they exploited stringing phenomena, its printing error. So next is a dual color mixing technique. So this technique can produce tone imagery by modulating the contour of each layer. So this modulation can be considered as layer shifting. The last one is switch vibration. So this printer has a large speaker under the platform, which vibrates the whole working area. So this vibration creates more pattern on the surface of an object. So this technique exploited over-extruding, so to express pattern. So these printing techniques allows users to print expressive and unique objects. Moreover, the printed structure with error becomes more accurate than a high-resolution 3D printer. In contrast, almost all 3D printers and its software are developed to prevent printing error. So they try to compete with expensive printer in terms of accuracy. So we believe these techniques are also an advantage of FDM. So to utilize the techniques, so we have to understand the technique itself and the way of controlling the parameter. Okay, here's our goal. To realize expressive 3D printing, so we comprehensively investigate the relationship between parameters and printed object. So we provide understanding of parameter setting as a distribution. So using this distribution, so we control an error as a printing technique. So with our technique, users will get expressive object. Okay, so we focused on two parameters. So the height position of the extruder and the amount of material. So these parameters are especially important for high quality printing. But as the number of parameters increases, the relationship becomes more complex. Therefore, we prioritize these parameters and use other parameters as a constant value. Okay, please take a look at this video. By combining these parameters, so we can see interesting behavior of material. Okay, let's look at the relationship between the height position and the amount of material. So in conventional software, to convert 3D model into printing paths, the amount of material can be calculated from several parameters, including layer height. So layer height is the height position of the extruder. So yeah, more simply, this can be regarded as a linear function of the layer height when the length of the load is 1 millimeter. So using this relationship, let's imagine a shape. It will be printed with various parameters. So for example, if the amount of material is larger than the height, so the load might swell to enclose the nozzle, or a thick load might be printed. So in contrast, if the height position is larger, so what structure is output? So moreover, what if we set an excessive value based on this relationship? So unfortunately, researchers have not been able to investigate all parameters, so because there are too many combinations in this space. And printing error have been out of their scope. Okay, here is our approach. To investigate this space, we consider this linear function to be in a polar coordinate form. So to decide a parameter set, we introduce two new parameters. These are theta and r. Also, we dynamically change our parameter while printing a load with a specific theta. By using this way, we can efficiently investigate numerous parameters. And moreover, by printing in this direction, the start of the height position becomes 0. So a printed load is always fixed to the platform. Okay, this is our experiment setup. We used Leapfrog-based FDM printer, and we used two conventional materials, so it's ABS and PLA, and sets the temperature of the nozzle and platform to recommended value. So the printing speed was 300 millimeter per minute, but in ABS, we also use 600 millimeter per minute to observe the effect of the printing speed. Okay, here is a video. So before printing a load, the printer extrude material a little. Okay, you can see the behavior of material. So we got a lot of rows, a total of 270 rows. The first, we classified the printed rows into 6 categories and named these rows according to the structural feature. We measured the position, so where the structure was changed, so based on this classification. We visually recognized such positions and measured using a caliper. Okay, next, by plotting these points on the space I presented, so we made a distribution. So it shows the relationship between a parameter set and printed structure. So small points in this distribution mean the position where the structure was changed. So in this presentation, I focus on one condition. Material is ABS, and printing speed is at 300 millimeter per minute. Okay, I quickly explain the feature of each load. First, this distribution has a blank space at the lower part. It means the printed thin loads are burnt out by the heat of the nozzle, so we cannot get a load after the experiment. Okay, first, the 3D printer can stably extrude material except when the amount of material is extremely large. In this case, the stepper motor, which is in the extruder, frequently steps out and the load becomes partially thin due to unstable extrusion. So next, when stepping out does not occur, our load is printed at a stable state. So the load becomes thicker as the amount of material increases. But we found a thicker load with ABS has a rough surface, like exploding small air bubbles in load. Okay, as the height increases, so materials are extruded with uneven structure. so we call zigzag load, obviously look like a printing error. But we focus on the appearance and rough surface, I think, which is difficult to print even by high-resolution 3D printers. Okay, on right side, coil-like load is printed by extruding materials from high position and material twisted on the platform before becoming stiff. And this widely spread out in the distribution. Okay, next, as the amount of material decreases, load becomes hair-like. So we have two hair-like structure. This seems to be printed depending on the amount of material. So you can see a rectangular area, horizontal lines in the distribution. So last one is, so this is almost the same with 3D printed hair, small amount of materials pulled by the nozzle and printed in mid-air. Okay. So with the distribution, we can control the behavior of material and structure. However, because the printed load can be affected by preceding structures, so an obscure area exists around the boundary of every category. So we currently choose stable parameters. For example, these are near the center of each category. So we also made distributions for other conditions. So you can see several differences. For example, by speeding up 600 millimeter per minute, stepper motor easily steps out. But also, in any case, hair-like structure can be printed depending on the amount of material. Okay, so we implemented 3 design systems to utilize our result. So these systems directly generate G-code, which is a series of commands to control 3D printer. So with the specific parameter we found. Also, this system requires several additional parameters, as the same with traditional software. So to set printable parameters, we investigate these beforehand by printing simpler structure, so load and slope and bridge. Okay, first, slicer software using zigzag load. So this can be used in the same manner as conventional slicer. Users import a 3D model to this system and set parameters. After this, the system converts the 3D model into printing path with zigzag structure. So to analyze whether support structure is needed or not, the system uses the additional parameters. Okay, here is our result. So this slicer software allows users to easily make these objects, fluffy animals, and do the load is suitable to print a fried shrimp. So next system is for emboss processing. So this system generates bumps on the surface using 2 parameters. So these parameters have the same height and different widths, namely different amount of material. So by assigning a binary image to the parameter, the system allows users to design characters and patterns. The last one, this is for printing a wavy seed. So this system also uses 2 parameters to express a wavy shape. So to generate smooth pattern, this system generates a path consisting of numerous micro movements and assigns a parameter according to each movement. So we applied our technique to other FDM printers and various materials, including ABS, PLA. So we found our technique can be applied to these environments, but we had to adjust several parameters, printing speeds, temperature, and our R and theta, so according to the performance of printer and material. Okay, finally here is discussion. So based on the investigation, we presented a new expression technique. So we provided the understanding of the parameters. So we made it clear that controlling parameters is equal to controlling the printed objects, so printed structure. So it's not printing error, it's about printing techniques, a controllable technique. And our technique can be used for texture expression without complex 3D modeling. So actually, everyone can make the same, so completely same object with a 3D printer, but 3D model has only information of its shape. So our idea can add texture to this shape. And finally, we received favorable responses from people. So they said it looks like handmade. So people accepted our technique as texture expression. So we believe that this comment implies the important aspect of personal fabrication. Okay, here's summary. That's my presentation. Thank you very much.
Hi. I was wondering, what do you think it would look like if to give these kinds of texture expression techniques to users that are doing design generally with 3D printers? Like, how would you kind of translate their design intentions into uses of these different texturing techniques?
Okay, thank you. I think texture expression is a really important aspect of 3D printing, but in current pipeline, we have to design texture using 3D modeling software. So it's sometimes difficult to model complex texture, but in our technique, so 3D printer can utilize a material property to express texture.
Yeah. So do you think that then you would have so how would that texture, how would users specify that texture expression is what I'm asking. How do you imagine that could work?
Excuse me, please. So how to use this texture?
Yeah, like how would, oh, sorry. How would tools, how would software, how would they add the texture to the design process?
Okay, so currently we implement software, so it's slicer software. So this software can convert 3D model, ordinary 3D model into printing paths to control 3D printer. So when convert 3D model, so the design system add texture information by controlling parameters that we investigate.
Yeah, okay. Thank you.